Okay, so we are to prove the power rule using the limit definition of derivatives. Recall before we start, the limit definition for derivatives states that let f be a function. The derivative function f prime is the function whose domain consists of those values of x such that the following limit exists. So f prime of x is basically equal to the limit as h approaches 0 of f of x plus h minus f of x over h. Let x and y be variables and let n be a non-negative integer. Now this is for the binomial theorem, which we will use to expand in different intermediate steps along our proof. So again, let x and y be variables and let n be a non-negative integer. Then quantity x plus y raised to n is equal to the summation from k equal to 0 to n of n choose k times x raised to n minus k times y raised to k. Recall, this n choose k is basically a concept in combinatorics called combinations, wherein there's a special formula for that which I will show later. Now we start with the first part of our proof. We want to show that f of x is equal to x raised to n. Then f prime of x is equal to n times x raised to n minus 1 for all n that are real numbers. So this is basically our goal, where we want to manipulate f of x equal to x raised to n to arrive at this derivative function. So recall, from the definition of the derivative, f prime of x is basically equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And by substitution, we get the following. So we get the limit as h approaches 0 of x plus h raised to n minus x raised to n over h. So it's basic substitution here, where we substitute the inputs of our function and we get the respective terms. Now, by the binomial theorem, this is what we use to expand x plus h raised to n, because we've simply substitute 0 here and in this function. What we get is basically an indeterminate form, because we get here x plus h as x plus 0. That's basically x raised to n minus x raised to n. That's just 0. And if you substitute h, you basically get 0 over 0, which is an indeterminate form. And remember, when you get an indeterminate form, what you have to do is to find some common terms or multiply by a conjugate or something, or really just manipulate the expression in such a way that you are able to cancel some terms. And in this case, our goal is to cancel h by some value. So by the binomial theorem, if we expand x plus h raised to n, we basically get the following summation. So this is basically equal to the limit as h approaches 0 of quantity, the summation from k equal to 0 to n of n choose k times x raised to n minus k times h raised to k minus x raised to n all over h. Now, this might look intimidating, but the thing is, we'll go around this and you will see how beautiful this proof is. Next, so basically expanding on this, if we expand our summation, remember the summation is basically just repeated addition, right? So we get the following expansion. So when our k is 0, we get n choose 0 times x raised to n minus k, which is just n minus 0, so we get x raised to n times h raised to 0, because again, by the summation, we have h raised to k, and in this case, our k is 0, so we get h raised to 0. And for the next iteration of the summation, we get n choose 1 of x raised to n minus 1 times h raised to 1, and so on, until we get to the last term, n choose n times x raised to n minus n times h raised to n. So all of these minus x raised to n over h. Now moving on, remember this expansion. Note that the combination, when you have n choosing k, this is basically equal to n factorial over k factorial times n minus k factorial. Now what's very interesting is that we actually arrive at really interesting constants upon evaluation of the combination. So on our first term here at n choose 0, if you actually substitute this, what you get is n factorial over 0 factorial, which is 1, times n minus 0 factorial, which is just n factorial. So basically get n factorial over n factorial, which is just 1. To show you a better example, when we choose 1 from n, we basically get n factorial over 1 factorial times n minus 1 factorial, which is basically n factorial over, this is 1, so n factorial over n minus 1 factorial. So if you think about it, the way you simplify factorials is actually just canceling different terms. So when you divide n factorial over n minus 1 factorial, you basically get n. Suppose you have 7 factorial over 6 factorial. All of the 6, 5, 4, 3, 2, and 1 will all cancel, and you're left with 7, which is basically, by generality, that's basically just n. So now, moving on, when you evaluate n choose 2, it's basically equal to this expression, n times n minus 1 over 2. And you can go around and really like evaluate this, but you will still get the same answer. Now, when we substitute our values, all of these constants that we have arrived in different combinations with respect to n, we get the following. So remember, n choose 0 is 1, so we get x raised to n, 1 times x raised to n, and h raised to 0 is just 1, so basically we're left with x raised to n. N choose 1 is just n, and then copy x raised to n minus 1, and h raised to 1 is just h. And for the third term, we have n choose 2, which is basically equal to n times n minus 1 over 2 times x raised to n minus 2 times h squared. And so on until for the last term. Minus all of these minus x raised to n all over h. So when we are finished substituting our different values for the combinations, respectively, we get something pretty interesting. So this term and this term actually cancels, right? So this is basically x raised to n minus x raised to n is just 0, so that's crossed out. So we're basically left with n times x raised to n minus 1 times h up to the last term here, as highlighted. Then we arrive with this. This is what we're left with. Now, it's pretty interesting that we actually have, for all of these terms, they actually have a common factor, which is h. Now, this comes in handy when we're trying to cancel our denominator h. Now, if we factor out h from this, we get the following. So we get the limit as h approaches 0 of h times n times x raised to n minus 1 plus the other terms. Now, we can actually see that we can cancel h. Now, this leaves us with the following. It leaves us with the limit as h approaches 0 of n times x raised to n minus 1 plus n times n minus 1 over 2 up to the last term. Now, by direct substitution, what's really interesting is since all of these are left with an h, when you substitute 0 to all of these terms, they actually cancel except for the first term, which is n times x raised to n minus 1. So by direct substitution, we get the following. N times x raised to n minus 1 plus n times n minus 1 over 2 times x raised to n minus 2 times 0. This is all of this is just basically actually 0. And the last term is actually even 0 as well, because 0 raised to any real number is just 0. So all of these are disregarded now, and we're just left with n times x raised to n minus 1. So by the limit definition of derivatives and the binomial theorem, we have shown that if f of x is equal to x raised to n, then f prime of x, or the derivative, is equal to n times x raised to n minus 1 for all numbers n that are real numbers. And the proof is finished.